Machine learning is one of the most used technology. So currently, all the companies are using this technology. But why? Because they can use their data to forecast their business. To keep that in our mind, we came up with a tutorial where you are going to talk about what is unsupervised learning. That is one type of machine learning. And we are also going to talk about what is clustering and what are the type of clusterings we have, right? So let's get started with the tutorial. But before start the tutorial, let me introduce that Great Learning has came up with a brilliant idea, that is Great Learning Academy, where you will get almost 80 plus free courses, and after complete your course you can claim your certificate as well. And if you want to do these courses in your mobile application, that is also possible using Great Learning app. So let's get started with the tutorial.
So we're going to talk about an unsupervised set of learning algorithms. So we're going to here discuss one of the primary methods of unsupervised. We're going to talk about what we call as a k-means clustering approach. That's a very simple approach wherein we're going to try and objectively select group of points that are closer and that are likely to be together. Right? That's the whole objective of k-means clustering, where we're going to try and put a certain set of points that are in patterns and put them closer together and set up the pattern and say, okay, they belong to group 1, they belong to group 2, and they belong to group 3. That's effectively what we are planning to achieve, right? Okay, now first up, when we have unsupervised learning, right, what's the primary and most functional most element is the fact that there is no target variable. Okay, now let me give an example. Let's say we have data about students spending time in their respective subjects. Can I identify studious from the weak students to some from the strong students? So that's an objective of that's the objective of unsupervised learning, where I don't have a predefined target set. So what I have is just the time spent by students in their respective subjects. That's an example of an unsupervised learning. Another more commonly used example is we have in the marketing, we call a model that we call as RFM. It stands for recency, frequency, and monetary value. Now, this RFM model is nothing but how recent did the customer come? What was the frequency of his visit to my store? And what was his monetary expense that he's spending on me? So that's an application. That's an application of unsupervised learning or clustering approach, wherein we are trying to do a segmentation. That's another approach. And we're also another approach is a pseudo AI approach, where we're going to talk about image recognition is an unsupervised form of learning, where I'm going to just train the model to pick up information. But what I have is basically I'm going to find out group of similar patches in data with a specific objective with specific highlights in mind, and try and cluster them and say, okay, they belong to this sort of a cluster one, which is a healthy or a benign tumor cluster. Now, so that's a combination of how unsupervised learning can be used for in multiple contexts. All right. The base is it's not classified or labeled. It's also where unsupervised learning will also talk about unstructured data. That's another level of complexity wherein we're going to talk about text-based analytics. So text-based information is also called as an unsupervised learning aspect. So anytime my target label does not exist, I call that situation as an unsupervised. So I'm going to find out patterns or groups in my data and then use these patterns or groups to implement, use these patterns or groups to identify these groups by a common center value and use my information around that center value. All right, that's going to be my objective. Now, one primary technique of unsupervised learning is what we call as a clustering technique. Now, clustering is nothing but I have group of data points that are together. I am going to group these points and I'm going to find a center value to these points and try and see if my entire group is responding or is a respondence of that group value. So that's a clustering approach per se. It's basically to club or find out group of points that are similar together in terms of a pattern and put them together in perspective. All right, an example is, so let's say I have data points here and I have data points here. All right, and I also have data points here. Now I want to cluster these together in terms of my best and worst customers. I'll say top customers, I'll say weak customers, I'll say better customers, I'll say the best better customers again. So this is kind of a segmentation can be achieved with my clustering technique. So basically take groups of data points together and put them in a single cluster with a center value that represents the entire cluster. So group objects, find similar objects, put them together, run this model. So that's what we call as a clustering approach. All right. Any questions?
Shyam, just wanted to ask, like we say that this is used in image processing as well as in
Mm-hmm.
other
Right.
options also. So just wanted to ask, like in image processing,
Mm-hmm.
suppose I talk about like if I need to understand what the alphabets are, then I have the whole set of data available with me, so
Correct.
I can categorize it. But suppose in case of I say that there's an face recognition system, so then
Right.
the in production there will be an unknown to it. So in
Correct.
that case, how it is differentiated?
Okay. So just one perspective to put into this, Nitin. So when you say image recognition, when you say alphabet recognition, so it immediately becomes a supervised learning problem where I need to know that this particular design belongs to pattern A. Now, when we talk about unsupervised learning context, when we say image processing, basically I'm trying to identify groups of objective points in a given data and analyze what they are. All right, I'm still have to still annotate them. What I am going to get from the clustering approach is going to identify, okay, these are the points that are similar together. What do they correspond to? These are the points. So in case of a medical recognition, medical image recognition, right? So if you have a tumor or a benign and malignant, so first let me identify patterns of objects that are together, and then use that to see, okay, is this a benign, is this a malignant, how are they responding to? So first identify patterns and then work with these patterns. So that's what we essentially mean by image processing or image recognition in a medical field. So for alphabet recognition, it again becomes an immediate supervised learning problem. It's not more of a unsupervised, because I already have an information that this particular image belongs to digit A. I have this belongs to digit B. Sorry, digit 1, digit 2. This belongs to alphabet A, alphabet B. So that becomes a supervised learning problem more than an unsupervised learning problem there.
Okay, just to extend it, like you say that even in case of the tumor is a benign or is a,
Malignant.
yeah, so even in that case there is some kind of a pattern available to me. Now
Right.
my question is like, if if you have trained it say to identify a particular person,
Mm-hmm.
so when you go into a production system, then there will be uh, new images to it. So
Correct.
how it will differentiate that uh,
Okay,
this is
so how it essentially differentiates is, so when it's slightly getting into technical aspects of image processing, right? So you're going to note this fact that when I talk about an image, I'm essentially going to talk about this aspect. So I'm going to talk about, this is an image, correct? Now this image is nothing but a congregation of pixels, right? Now each pixel is basically a shading. Now if I write the digit 9 in this pixel, if I write the digit 9 here, all right, let me write this multiple times. Now, if you notice, there are certain pixels that are shaded well, all right. For example, this pixel is shaded well, this is not so shaded that much. So you will see this, there are pixel cells with certain intensities. So image recognition essentially is how much is this image intensified, how much is the color intensified. So that's basically another category of problem, all right. So if you want to talk about production identifying this, so basically this is my input. So my data set would look like, for row 1, all right, I'll have some x number of inputs. So pixel 1, pixel 0, pixel 1, pixel 2, all the way up to pixel n. I'll have the responding shadings. And this is, I will try to see which cluster does this belong to. Does this belong to a specific cluster? Is there a pattern that the digits are holding? Is there a specific pattern in the given input? So that's essentially what we call as a unsupervised learning for a machine, for an image recognition context.
So just to extend it, now you have a 9. Okay,
Mhm.
I have trained it on 9. So it will try to find out the patterns where it is 9 or it looks like
Correct.
it. I am saying that if it is not 9,
Okay.
so how will it understand if I don't give it 0, 1, 2, 3 anything as an input in
Okay,
the
so
model?
what it will identify is, if it's unsupervised, what it will identify is, it will identify that, okay, I have a set of shading along these pixel lines. Okay. Now let's look at this closely. I have a set of pixel shadings that respond to these lines or these boxes. It'll try to pick this pattern and give me a separate value. What the unsupervised can tell me is not if it is a 9 or a 10, but what can tell me is there is a pattern that has this shape. there's a pattern that it has this specific shape, right? There's a pattern that it has this shape. So what the unsupervised is going to tell me is identifying these patterns from the data and telling me, okay, there is a pattern that exists for, there are so many patterns that exist. If I want to talk about clustering, there are so many patterns that exist in this cluster. So that's what essentially the k-means will ideally tell you. Does that make sense?
So when I have trained a model and I have given it into a multiple nines to it, so it will identify across those patterns that okay, it matches one of these and it goes 9.
Correct.
But but I have not told him what 2 is. So when I
Okay,
give
so
2
what
to
happens is, it will try to put 2 to the nearest. So if I don't have 2 in my cluster, right? If I don't have 2 as a centroid, it will try to put 2 to the closest object it can find. K-means will essentially work on a centroid algorithm approach. So it will try to put 2 to the closest objects it can find, the closest centroid, the value of it corresponding to a closest centroid that it can find. There will be misclassifications in that context. So when you're training it, your unsupervised is going to pick patterns. It's going to pick that 9 has these patterns, that they have a centroid of the value corresponding to so and so pixel shadings. 2 has a centroid that is corresponding to so and so pixel shadings. So the 9 and 2 are something that me and you define. For the machine, it's just a pattern. It's a pattern of shading. Okay.
that I have understood.
Yeah. So let's say this is my input, right? So if you understand k-means, k-means will tell you that dimension 1, d2, variable 2, variable 3, all this. So you'll have a respective shading, correct? So you'll have a centroid, correct? That's how the k-means works
Yes.
with me. So the k-means will have a center. So
Yes.
objects that are closest to the center are tagged to the centroid. So you will have some, if I talk about a 2-dimension, right? I have these points and I'll have another set of points here, correct?
Yes.
So a centroid will be here. A centroid will be here. Another centroid will be here,
Yes.
right? Now, what does a centroid essentially comprise of? The centroid is nothing but in these 2 dimensions. For these 2 dimensions, so centroid 1 will be for this dimension, for this dimension of 1 and 2. What is the average value of x1, x2 that it corresponds to, say 100 or 200? Okay. Centroid 2 again will represent x1, x2 with say 150, 20 and 10, right? So I can identify this pattern has a centroid, right? Similarly, this entire problem is broken down into an n dimension. I'll have n dimension. The centroids of 9 will be different. The centroid of 2 will be different. Centroid of 3 will be different based on the input patterns that it sees. So it will try to identify the pattern of input that it essentially sees. That's how the algorithm functions.
Yes, I understand that.
Mhm.
Uh,
So your
okay,
question is, what if it does? What if
my
it?
question might be I might be wrong in something, but my question is slightly different. See, I understood that 9 it has a pattern. We are identifying that 9 as a pattern.
Mhm.
Now my question is when an unknown comes to it,
Okay, so
which I
something.
have
Let's say
not
I have
classified.
a 3 coming in.
Yes. So now what it does is, how does it categorize it as an unknown?
Puts 3 for the unknown. It completely does not see, right? It tries to put this 3 to the closest centroid it can find. So the input value to the closest value it can find, it will place it will place this object to the closest centroid it can find. That is how it works.
So how does it takes into account that okay, these patterns are not available in my data, and that this is a new pattern which has to be categorized and
So
appended separately?
for unsupervised learning, there is no specific pattern. So it just has a value. It has a centroid. So when you train it, right? When you train an k-means algorithm, so you're going to create these center values, correct? With me?
Yes.
Right? So k-means when you train it, it's going to create these center values.
Yes.
Now, from the center values that it creates, okay, any new point that objectively comes in is going to have some input.
Yes.
It is going to compare the distance between this point to this center and to this center and to one more center and tag it appropriately to the center that has the lowest distance. Does that answer your question? So there is
So
no pre-trained label here. There is no pre-training that says this pattern is belonging to group 3. That becomes a supervised learning. So what k-means will identify is a new point. If, for example, this image 3, or let's take an image 4, for example, right, is going to have some pixel shaded. So it is going to have a data input that looks like this, correct? You understand this input? Input I'm tagging here. Does this input make sense in terms of pixel shading?
Shyam, midway, can you tell me something about unstructured data? Like in ML terms, what it means? It doesn't follow a pattern or something like.
Not precisely. So when you say unstructured data, text is an unstructured data. So when we say right, we say text is unstructured. So I can say this is an input, right? So the machine has to understand that this is an unstructured, because if I give a direct text to a machine, it cannot understand anything, any input as part of it. There is no information it can correspond it to. So this has to be converted from a text form to a machine readable numeric or a number based form. That is what we call as an unstructured. So image is another example. So image directly, if the machine cannot recognize an image without understanding what contents it has. And even if it understands the contents, how will it understand these contents? The same problem that me and Nitin were discussing. So if I have a number 9 here, how will it recognize this number 9 as number 9? Right? So the question, the way it essentially does is it has to break this number 9 down in terms of a pixel shading. And from these pixel shaded values, it will train and learn that if these pixels are highlighted, then this corresponds to the probability of number 9 is so and so. So number, it will rank the probabilities from 0 to 10, 0 to 9, and find out which is the highest probability closer to this.
So I think what maybe Nitin, you can correct me if I'm wrong, but I think what Nitin is trying to ask is that since in the unsupervised learning we do not have target labels, so that means that when I have training in the training stage, the training data, you do not know that what are the exact number of labels would be. For example, if you're talking about the digits, then we do not know that
if I'm going to have 0 to 9 or much more than that,
9 or just 0 to 8 or 0 to 7, something like that.
Right.
So since unlabeled data, it is quite possible that your training set do not have a pattern line at all. Right. And now you actually deploy that model into production and you get an image which is actually representing 9. What in that case?
Okay, so if it is representing if the actual deployment has a number 9 as a representation, right?
Yeah.
When we train the data, so if you get a number 3, let's say I'm training on number 9, I'm training between 0, 1, 4, and 9, right? And let's say I'm training on this, and I get a number 3. All right. So the shading or the pattern that number 3 exhibited will be different, will be completely different to any of this that I've seen earlier, correct?
Right.
So what k-means ideally does is, when I'm training it, if I say there are 4 patterns in it, or there are more than 4 patterns in it, there are more than 5 patterns in it, it will create appropriate number of centroids.
Right.
So that is what we call as a k. The k is the number of centers I'm defining in my data. Either I choose the inertia to choose the ideal centers. Either I choose it based on the elbow method, or I just randomly choose an arbitrary number of k that I want, and I set it up. Right. So when I define that, my model is going to be in my data, my structure is going to have some n k number of centroids.
Right.
Right. So in my production, if a number 3 comes in, so the number 3 is going to correspond to an array of values. So this array, I'm going to compare the distance that this array has with all the centers, right?
And it will be misqualified depending on...
Yes, so it will be misclassified. Definitely there will be a misclassification. So that's the problem with unsupervised learning. I don't have a specific target to measure it against. There is no measurement index to say this is accurate, this is inaccurate. So it is basically a pattern.
So I was just asking that because it means that it has to be kind of a continuous feedback kind of thing where you qualified few things, then you actually bring this new set of data to your training data. And
yes, so this is what you just talked right now. So what you just spoke about right now, Rohit, is what we call as the neural network models, or a structured neural network, or a recurrent neural networks, or things like where there is a feedback loop.
Okay.
So we call that as a reinforcement learning, where there is a feedback that goes from the output back to the input in terms of how classification accuracy has been created or not.
Okay.
So that sort of a feedback becomes a deeper neural network architecture. We call that as a reinforcement learning model. Okay, so Chitra, one point to add on your note, right? So you mentioned that the number is a structured form of the image. So I beg to slightly differ in that point, Chitra. The reason I say that is the number is, so I as a user, I as a human, or you as a human or a user can understand anybody writing 9 in different ways. I might write it 9 with a broken 9. I might connect the loop. I might not connect the loop, right? So what happens there is you can read it. You can read the image. You can understand this image. Now to the machine, it's nothing but a mere input of patterns of respective cells of pixels being shaded, and that pattern per se is what is being understood by the machine to say, okay, the probability if I see this pattern is 70% towards 9, 10% towards 1, and 10% towards 8. Remaining this percentages split across the other numbers. So that is what the pattern is essentially corresponding to. So that is still an unstructured problem that we are going to define. So the data is unstructured, which means that I cannot natively use an image to an input and say, okay, learn from this, and the machine can work from it. So there has to be a set of input steps that converts this image into a reference value, and then that reference value has to be learned by the model to make an actual prediction. Right? Does it make sense? Does it answer your question? There are two types of clustering per se that we essentially look at. One we call as the hierarchical clustering, and the other we call as the k-means clustering. So hierarchical clustering is an agglomerate. Basically, it's nothing but it's an aggregate-based clustering. So if I want to talk about hierarchical very quickly, it's part of your discussion next week. We have the dendrogram approach. So hierarchical clustering basically starts with every data point as a cluster and then slowly aggregates up back into a single cluster value. So this is where my hierarchical clustering, what we call as a bottom-up approach. So it starts clustering for these points that are the points in the hierarchy in the chart. Closest points first, closest points first, closest points first, closest points first, and then the entire thing. So the hierarchical clustering is that kind of an approach. K-means is a little more different, where it takes so K-means is a iterative algorithm where it starts with random centroids. So K-means will start randomly assigning some centroids across the data point. So it has a random start center to the entire algorithm approach, and iteratively it will try and converge. It will try and converge from this to the center. Again, from this point to the center. So it will try to converge and say which is the closest to the actual value. So the K-means is an iterative algorithm which basically converges on an iteration. So it will first start from a random start point and then try to initialize and then check the cluster that it is closer to, check the distance of the cluster, and then converge more closer to that cluster. So that is how it effectively works. All right. This is your K-means approach as a hierarchical clustering. Now we are going to talk about different distances being used. So one of the most common distances we are going to use is the Euclidean distance. Now Euclidean distance is the square root of sum of differences between the x and y in each dimension. So that's basically we're going to measure x2 plus x2 minus x1 the whole square plus y2 minus y1 the whole square plus z2 minus z1 the whole square. So based on n number of dimensions. That is the L2 norm. The L1 norm is nothing but just the sum of differences. Right, x2 minus x1 plus y2 minus y1. So that's basically your L1 and L2 norm in the Euclidean distance. So Jaccardиan distance is used to find out objects in similarity. So we use the Jaccard distance. It's 1 minus ratio of sizes of intersection and union. So basically, you want a ratio of intersections, so the number of objects that are closer to that are matching it, divided by the union. So number of objects are the complete entire set. So 1 minus the ratio of that size. Now Jaccardиan distance is used where we are going to talk about the recommendation engine. So that's another distance set that we're going to use in recommendations. So for movie recommendations, we use a Jaccardиan distance. Now cosine distance is another mathematical distance. It is a cos theta angle distance. So cosine distance is defined as A dot B. So it's actually a vector magnitude of A into magnitude of B. So this is what we call as a cosine distance. Okay, cosine distance is used again in it's another application in word engines, word similarities, Chitra. So for example, you have this package that we call as glove or word embeddings. So if I want to find out a word that is very similar to its nearby objects or very similar to words that are closer to it, we use a cosine distance. So we say, okay, this word may be closer to this word based on these aspects. So based on the cosine distance or cosine similarity is what we call it. So that's a text-based similarity. Again, most of these distance that you see, the Jacquard cosine edit, most of these are predominantly used in text corrections and text management. So we use word vectors, word vector embeddings to do the text, the spell corrections. Edit distance, cosine distance comes in specifically there. All right. The k-means clustering is what we were just talking about it. We didn't talk about k is the number of centroids that we choose. Now, ideally, the number of centroids is to be chosen by what we call as an inertia. So inertia is nothing but, let me just explain this concept of inertia here. Okay, so let me just try and explain the concept here. That I'll see it to make as much of sense. Let's say this is my point. Okay, now this is my data clusters. Let me draw this here first. Now let's say I'm going to draw the elbow method here. All right. Now the elbow method uses what we call as inertia, or in other terms we call this as sum of squared distances. Okay. Now this is nothing but a very simple fact that, okay, now to this data, to this set of input, what do you think is the ideal number of cluster size? So ideal k is 3 because this is only a simple 2-dimension. I can easily see it. What if there's n dimensions? So what happens to the sum of square distances? Let's say I set only one centroid here. Okay. Now let's measure the distance of this point to all the objective points in the cluster. So what do you think will be the sum of distances? Just let's say if I treat the entire data as one cluster, if I just have one centroid, what do you think will be the distance that it carries? What happens if I set the number of clusters to 2 in this context? Let me say it starts with a very large value. What happens if I set the number of clusters to 2? The sum of square of distances for, instead of one cluster, if I set it at 2, what is going to happen to this? If I set 2, maybe this is maybe the point, this may be the point. The distance, the sum of square distance between this object to this point and this to this point, will it come down? Will it not come down? So I'm going to have a reduced distance. What happens if I set it at 3? It is going to even further come down. But beyond 3, the sum of square distance is not going to come down and it is going to start tanking. So this part is what we call as the elbow. Elbow is a point at which where the sum of square of distances is the lowest is a solution where I find a steep change in the sum of square of distances value. Does that make sense? That is what we call as inertia. Inertia is nothing but the distance it carries to the sum of square distance it carries to the centroids, specific centroid. Now this is the elbow method I have. All right. Now I'm going to go ahead and we're going to start implementing a quick clustering approach to a data point that we have. All right, to a data set that we have. Now this data set is going to be about, it is a psychological study. The data set, if I want to give you a prelude to the data set, it is nothing but a psychological study. Okay, it's a psychological study that effectively talks about what is the fatality rate of somebody's thought process, what is the simplicity in thoughts that somebody has. Now simplicity here is the black and white distinguishing thought. So am I looking at black as black and looking at white as white? And what is the depression quantum somebody carries? So these are all three things that ideally is looked upon in a psychological study. Now we're going to analyze this data. Now if you understand this, none of this data, none of the metrics I told you right now has anything to do with the target. So I don't have a specific target to say what psychological state this person is. This is a very simple point where it says there's no target variable, but we're going to find out what are the groups of people that I have, how many groups of people are ideal, what are the groups of people I have in my data. Okay, so that's effectively what I'm going to set upon and do. Now if I notice, this is my data, so I'm going to have this simplicity, fatalism, and depression as the key inputs. This adjusted simplicity, adjusted fatalism, adjusted depression are not going to be my key inputs right now. I'm not going to worry about those parameters. So if I want to give you a little more context about this data, I'm going to give you this piece of block that I have. Now, this is the data source. So basically, it is used for black and white thinking, where we call this as our approach to somebody's approach to simply saying how are they perceiving things, right? Now, this is also the quick context of the story. It is common for people to think as black and white events to suffer from depression, cyber square, etc. This is a new way of thinking. All right. So what I'm going to find out is find out groups of people that are similar together so that my treatment can be as appropriate, or my approach to this to the problem that they're facing can be appropriate, or different ways of essentially handling these people. So that is what we essentially look for in this model. So I want to find out from my data about how can I use the simplicity, fatalism, and depression parameters to look at these people and say, okay, can I look at this? Can I solve this person's problem that they have? Okay, can I first identify who these group of people are, and then make my relevant inputs as appropriately. Now, one thing I want to quickly draw to your attention is information. If you notice, there is something very different about this. So your mean and standard deviation for simplicity, fatalism, and depression are exactly equal, right? So that's another quick point I want to add to k-means. If your data has a different mean to each of its column and the standard deviation is different to all the columns, then we must normalize or standardize the data before we proceed towards the model building aspect. All right. Okay. Now, my columns, my parameters in my data.
Just one thing, when we call when we say it's different, standard deviation. So what is the deviation that is considered?
Okay, so the deviation can be any value, Nitin. Just to quickly put, but the same answers of both questions. Both of you are raising the same question. The standard deviation or the mean can be any value, but the mean of all my columns must be an exact, more or less, an equal value, and my standard deviation of the columns must be an equal value. It can be 0.5, it can be 2.5, it can be 10, it can be any value, but it must be a constant value that is precisely the same. If it is not, then the data must be standardized. Now, if you notice, the standardization is a property. If I talk about the standard normal derivative z, it is nothing but x minus mu by sigma, which will convert my data to have this property of mean equal to 0 and standard deviation equal to 1, right? So that's something that I have to apply. Does that answer your question, Nitin and Rohit?
No, so can you explain that again? Means are you saying that the mean for all the attributes has to be same and
Yes.
standard deviation?
Yes. The mean has to be the same. The standard deviation has to be the same constant value. That's the undertake that you have for k-means. That's an expectation for k-means.
Okay. And how do we actually, is there any library that actually help in standardizing?
Yes. So you have the standard scaler, right? A standard scaling. The standard scaling will convert the data to have the singular property where the mean of all my values will be closer or approximately 0. The standard deviation will be 1. Right? That's a feature scaling. So that can be applied.
Shyam?
Yes, Nitin.
I think I tried to use standard scaler library, but I was not able to use it. Can you just show it over here in this data set?
Okay, this data set is already standardized, but yeah, I can surely show you the standard scaler here.
Also, one more thing, you said that if your standard deviation is different and the means are different, then you need to use this standardize the data.
Correct.
So just wanted to ask if there's, because I was going to ask this question. I had used I think first of all, is it model dependent or it is model independent? Because I had used just logistic regression.
Okay.
Now, without it had a different data which was having a different ratio. So might be one was between 0 and 1, and other was having a range from might be 200 in the range of the other attributes, or in the range of that kind of a data.
Okay.
So if I try to use if I didn't use any kind of a scaling or any kind of a standardization on that data, and I use when I use build the confusion matrix on the based on the recall and the precision value, it was not varying. in the sense that if I use the standardized scaler, only it was getting worse, not improving.
Okay, I think I remember you sharing this point during one of
Yes,
the project discussions, correct?
yes,
Okay. So Nitin, can we just take this offline? I just wanted to look at the data and the solution that you built. So before I make any specific comments on this, can we just look at the data and then look at the solution for
sure,
this?
sure. So basically, was is there any kind of a definition like you shared over here, like that standard deviation has
Right.
to
So
same.
for logistic regression, there is no specific input that says the standard deviation has to be one. So that's specifically for k-means. Only very specific algorithms have this expectation. So the regression algorithms expect that the target variable to be normally distributed. So that's pretty much it. There's nothing else that I'm going to specifically insist on that parameter there. So when you standardize the data, the mean will be approximately or closest to 0. All right, and the standard deviation will be will be 1, or in the third or fourth decimal. We usually don't worry about the third decimal. So we look at this. The property of this data is the standard deviation is 1 and mean is closer to 0. So it's a constant value. So that can be used to build this k-means algorithm on top of this data.
So in other sense, standard deviation is basically the area under the curve. So we are just trying to get say the number of samples for each data into an equivalent category.
Right. Yes. So standard deviation is not standard deviation. If I talk about a normal distribution, is a dispersion between the mean. So how is the data distributed around the mean? So I'm trying to get that dispersion as a constant value to all my data columns in such a way that ensuring that the calculation that I'm doing. So it's basically Euclidean calculation, right? So the Euclidean calculation essentially takes care of a value that's very precise. That's the reason we do this.
So we are just getting the means to a common value so that the
calculation is more appropriate there. Right? It's the calculation happens within a specific range. It is not dispersed or diverging too far away. So what I'm going to do is I'm just going to drop this other columns right now that I'm not going to use. So I'm going to use adjacent simplicity. I'm going to drop adjacent fatalism. Adjacent fatalism I'm going to drop, and adjusted depression I'm going to drop. Okay, now my data is ready to go. Okay, so a quick check. I can either use a KDE or a histogram. Here I just want to look at a KDE for a kernel density estimation. That's it, right? This is my diagonal for this specific model. So if you notice, there's a relationship between what simplicity has with fatalism and fatalism has with depression, and so on. So this is nothing but a sort of like a grid where we can look at each value. Now, here's a part where I'm going to calculate the ideal centroid. Okay. So I'm taking for 15 values, I'm taking for range of 15. I'm iterating between 1 to 15 clusters or 1 to 14 clusters. And I'm getting the, so let's say I'm getting the centroids of this and I'm calculating the inertia. So inertia, remember we tell is a sum of square of distances. And I'm just calculating the sum of square of distances here to, now my inertia is calculated. What I'm going to do is I'm just going to simply do a scatter plot. And I'm going to look at this bow. Now, if you see that ideal is either 2 or 3 clusters, beyond which I don't see a significant change or significant decrease in the number in the centroid values. Remember the same problem I told you earlier. I just showed you an example where I have to have more than 2 clusters, more than 3 clusters, more than 4. Beyond a certain point, the sum of square of distances is not going to decrease at all. Now, that's something that we have to remember in that essential model. Okay, does it make sense? Okay, so here I'm stating that 3 clusters is ideal. Let's go with 3 clusters and using this n in it is the number of initial centroid points that I want to start off with, and from these centroid points calculate, try and converge to a specific value. So I'm going to take a certain number of iterations to do it, and I am going to essentially achieve this model there. So I'm just going to fit my data here, and to this fitted data, I am going to now I'm going to the error earlier was because the data did not have. So the error, if you're talking about here in the previous line number 26 of Chitra, because I've already dropped adjacent important, adjacent fatal, and adjusted depression. So that's not going to exist in my key. So the Python will throw an error saying that that key specifically does not exist. That's the reason it threw that error. And these are my cluster centroids right now. All right. So 3 and even up to 4, I will say is agreeable. 2, 1 and 2 as a major jump. 2 and 3 still as a jump. 3 to 4, I will still consider. So that's still acceptable, right? So I'm going to say 3 clusters, and I can be right or wrong. Let me be honest here. I can be right and or wrong. So that does not mean anything here, because I'm essentially giving you this point where I'm saying true or 3. I don't know which is the correct answer. I'm just hoping that the elbow method is giving me the ideal cluster size. So I'm going with that aspect and saying that, okay, I understand that this is how it works. So this is what we have. Okay. Now this is the key part. This is the key aspect of k-means. So you're going to look at the centroid value to maybe name, label, or come up with values of your cluster. So either way, there is not a problem there. So you can just label or value, set anything that you would like, and go with this, right? Now, what I'm going to show you next is how to insert this label into your data set. I'm just going to show you how to insert this data how to insert this label into your data set by adding as a separate data frame. All right. Now, if I print this centroid DF, you understand? Okay. So now I know that there are 3 groups or 3 patterns in my data, right? And I'm going to use these 3 patterns, and I have 3 such patterns in my data. I know that this is a group. Okay, but what to name them, how to name them, that it is up to left to the subject expertise. Okay, now if you notice, every target here is labeled based on the centroid that belongs to. So I have 82 data points. All 82 data points right now tagged to one specific label group that I have. So I'm going to now create a data frame, and I'm going to join this data frame there. Okay, this is your final output that you're essentially going to take. So I have each group below, each observation tagged to a specific group, and I now can analyze. Now from here, from an unsupervised perspective, I now have a group value. I know what each group ka average value is, which means that what is it representing, which group, where does it belong to, and how does this specific observation, how to tag or name it, that I can leave it to the experts, subject matter experts. But I now can understand there are 3 patterns, 3 to 4 patterns in the group, or even 2 patterns, and I can work with creating these patterns in the data point. All right. Now this is what I had in store for you today. Any questions?
Can you just, I just missed out. Can you just explain these values that were coming out in each data set?
Can
in
I,
each record, that 0.92, 0.359.
Yeah, this one?
Yes.
Do you mean this one?
Either of them, because I think they're related.
Yeah, this is the raw data. So what you see here is a raw data, Nitin. So this is the actual data frame, and the k-means is essentially tagged, say, based on the centroid. I told you it calculates a distance, it creates a cluster, and it tries to set this point in the middle of the cluster, correct?
Yes.
Right. So it has now calculated that this specific data point is closest to the first cluster, right? So that is how it is tagging it. Basically, when it is training, it is tagging based on Euclidean distance. It will create a centroid, find out groups in the data, and merge this information to the centroid group of the data point. That is what you see here as value. So it's the raw value and which group it belongs to.
It is showing the distance of from simplicity cluster.
No,
and
the raw data. What you see here is the raw data.
Okay. This is the data values for each.
Yeah, this is the actual data value, the absolute data value. All right, so a couple of things. We're going to talk about what hierarchical clustering is, and then we're going to look into what PCA is. All right, so pretty simple stuff. Hierarchical clustering is probably one of the most simplest algorithms. So what we have is, let's say I'm going to talk about a clustering approach that uses complete data, and I'm going to choose only the cutoff based on the top n features. I mean, top or the hierarchical list that I have. Okay, now what do I mean by that? It's very simple. Okay, so let's say my hierarchical clustering treats my entire data point as a single unanimous value. So it ideally treats the entire data. So let's say I have a data point that I have here. Now let's say I have a data that's like this, and hierarchical clustering is purely based on the distance. Now it is going to calculate the distance from this objective point to all the other neighbors, from this point to all the other neighbors. So ideally it will be a distance matrix by where it's going to be row number 1, row number 2, 3, 4, 1, 2, 3, 4. So it's going to calculate what is it's not going to calculate 1 to 1, but it's going to start calculating what's 2 to 1. All right, and not 2 to 2. So it's going to be 2, 3, 5, and so on. It's going to just fill this matrix. Now based on this, what's going to happen is initially all my individual points are treated as a cluster themselves. Okay, now all my points are initially treated as cluster themselves. So what happens is it's going to start combining clusters, and the map of it is going to look like this. And initially the hierarchical clustering map with its, say, let's pick the height, is going to start looking like 1, 2, 3, 4, 5, 6, and all your points. So it's going to combine 1 and 2. It's going to combine 3 and 4. 8 is going to combine whatever next the nearby object is. So if it's nothing is there, it's going to stop this. And what it's also going to do is, next level, it is going to now combine the next set of nearest objects like so. In the next level of distance value, it's going to combine objects so. All right, so it may combine, say, 5 and 6 here, and so on. So it from here it is now going to start combining or creating a single cluster value by joining these two clusters together, and or rather, which are the next two that are closest together, maybe these two together and then these two clusters together. So it is now going to combine, say, 1 and 2 with 3 and 4, and then 5 and 6 to this. So it is going to keep combining individual data points as back into clusters until it reaches one single whole cluster. That is what we call as a hierarchical clustering. So this is hierarchical clustering as top down and the bottom up approach. So this is what we call as a bottom up approach. So basically we're going from the bottom, from every individual element to the final most value. So this is called as, this is your hierarchical clustering in a nutshell. So it just calculates the distance from these objects slightly differently. So we have the linkage method. So you have the complete linkage, or we have the median, the average of the linkage. So a lot of these different things, and it essentially works around that way. All right. So this is what we essentially say is your hierarchical clustering method. So when we have the measuring distance between clusters, we have what we call as a minimum distance. That is a single linkage value that we're going to look at. And the maximum distance, which is the complete linkage, the average distance between the distance between the cluster points. If I'm clustering more than one, right? So if I look at, I'm going to cluster more than one. So what is the average distance between these two? Combine that with the next nearest objects that have the similar distance, and then put them in the map together. So this is called as average. And centroid, which is nothing but the center of this entire cluster segment, and the watch method. These are all different cluster linking methods that we have. The complete linkage method, it just kind of finds the largest distance between the pair of records A and B and combine to A and B respectively. So it kind of joins, as I said, the height of it is nothing but how it kind of joins them together. Is about how to implement it. So you have inside the cluster, we imported k-means last time. So here you're going to use this agglomerative clustering package that gives me, okay, the number of clusters I want to create, the affinity, it should be Euclidean distance, and the linkage can be either average or whichever I'm essentially choosing. So next comes your principal component analysis. It's a very, very interesting technique. It's a very, very complex technique, but it is also a, yes, somebody has any questions?
I wanted to ask, like, basically, scaling is basically converting everything into a
that's core value.
Uniform distance, where it
Correct.
can be scale of 1 to 100 or 1 to 1, but everything on the scale here. So change it, 1 unit will be equivalent for everything.
Correct. So
and normalization is basically converting
values
again a normal, Gaussian distribution, converting into a Gaussian distribution.
Correct.
So my question is, we can use either of the two for this, or it has to be scaling. And second thing I wanted to ask is,
Mhm.
suppose we are using a PCA as well as some model building for, say, at an initial level before PCA. I want to build a certain model which uses, as let's say, K means
Okay.
also. So
Okay.
when I use K means, I might do a scaling feature on this data set.
Right.
So now, do I need to normalize the data while using uh, 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 feature, say PCA, or vice versa? So my question is like,
Okay. So when you use standardization already, do you want should I normalize the data? Is your question?
yes.
Ideally one of these two. All right. So if my data is going to work on Euclidean distance principles, I would scale it rather than normalizing it. So at any point of juncture, if I'm going to use a data, for example, your k-means or knn, these algorithms are working on Euclidean distances, basically calculating Euclidean distances. Now, in that context, I would have this data standardized as opposed to normalized. Now, where I'm going to use normalized, or it kind of gives you between this Gaussian distribution range, is when my data independent values have a lot of these discrete 0 to 1 values, and I want my current column also to have this normalization value. So I want the current column to be a representation between its own value between 0 to 1, keep it restricted to itself. So that's where I'm going to use a normalization as opposed to my standardization with any set of algorithms. Does that answer your question, Nitin?
Uh, Partially yes, but if say I have say two or three models which I am trying to run on a given data set, and one of them uses uh, one of them can basically work on a scaling factor.
Right.
So once I have done scaling,
Mm-hmm.
now I've come on to a second model. So
Right.
is it required to, if it's not, is it required to do the normalization again on those features on the scale data, or I have to?
On the scale data, you will not normalize. So on a
Okay,
data that's already scaled, I'm not going to normalize. The reason we scale it is there's a behavior that we expect that it has to have a constant mean and a constant standard deviation. K-means has this expectation, and if you notice, KNN also has this partial expectation where the data has to be in a specific format. So because the K-means or KNN is affected by variance. Now variance, when I say this, it's just basically the spread of the data, right? So given that if I have already standardized the data, I am not going to go ahead and normalize it. That will not make sense in that specific spectrum. So to answer your question with probably a little more simplicity, no, I'm not going to I'm not going to normalize the data that I have already standardized. I might keep the raw and I might normalize the raw data to work for that algorithm, but I'm not going to standardize, I'm not going to normalize the standardized data. Okay, now I'm going to talk about principal component analysis. Now there's another dimensionality reduction technique. It's called as factor analysis. Now, the prime objective of principal component analysis is, if you remember one of our questions, one of our model expectations that the data should not exhibit multicollinearity, correct? That was one of the conditions that linear regression specified. Now, I also want to use this algorithm if I have too many dimensions that I'm not able to use, that I want to use, but I cannot directly fit them into an equation or kind of come up with individual variables, because statistically they might be insignificant individually. But in perspectives of how these variables evolve and in perspectives of how they uh, help me understand my model, it's going to be quite a lot. Now, given that I want to do kind of reduce the dimension, so this is a method that we call as feature engineering. One of the methods of feature engineering is feature elimination. The other is feature selection, and the other is dimensionality reduction. So here we're going to talk about dimensionality reduction, where I'm going to reduce the number of dimensions that I have and work with a subset of our dimensions. Okay. Now, the components PCA is nothing but it will transpose or kind of place the entire data using this eigen decomposition. It kind of gets this covariance matrix. It kind of uses this eigen decomposition that loads variables onto a set of principal axes. It essentially helps me to kind of place data on an axis. And remember this aspect: the principal components are always perpendicular to each other. If I look at if I'm going to replace a value, it is always going to be perpendicular. The PC1 is always going to be perpendicular to PC2. The principal component 1, it is always going to be component to perpendicular to PC2. This PC1 will load a specific set of variables to its dimension. PC2 will load a specific set of variables to its dimension, but they will always be perpendicular. Even if I have more than one PC1 and PC2, PC3, all of them are going to be perpendicular to each other. All right, and we're going to use if I want to choose a proper principal component, I'm going to find a continuation of how much of covariance the data explains, and choose the specific number of principal axes based upon that value. All right. Now, first, I'm going to measure the variance and the within the dimensions and covariance among the dimensions. All right. So if I want to talk about total variance and covariance, it's a very simple formula. I'm going to talk about x minus x bar into xi minus x bar. All right. That's nothing but x minus x bar the whole square. And the covariance of between two variables is x minus x bar and y minus y bar by n minus 1. So summation of all these values, it's kind of an average value, right? So the variance is how the data is spread across, right? The variance is nothing but how far the data is spread across. The covariance is how tight is two things knit or bound together. So that's called the covariance. All right. Now, the math behind the principal component analysis talks about calculating the transpose matrix, multiplying that with the identity matrix, kind of a different story altogether. But in a very simple essence, we're talking about placing certain set of variables on a specific principal component and placing another set of variables on another principal component. And I'm going to use these components instead of using the existing set of independent variables, right? And I'm going to choose this a number of principal components I need by what we call as a scree plot, right? So we have something called as a scree plot, and I'm going to use this scree plot that kind of, if you remember in k-means, we had this elbow plot. It gave me an elbow where I have to choose the number of clusters. Similarly, in principal component analysis, I have something called as a scree plot. Now, the scree plot is going to tell me at the elbow where I have to use to kind of get, okay, this is the method I'm going to use, and this is how it is going to work. This is the point at which I'm going to say the number of principal components are sufficient to explain the percentage of variance or the proportionality of the variance that these particular variables carry. I'm going to use that method to identify and say, okay, this is where I can use, right? So I'm going to arrange all eigenvectors along with corresponding eigenvalues in descending, plot a cumulative eigenvalue graph, and the eigenvalue with the least insignificant can be removed from the analysis, right? This is what we call as a scree plot. Now you're going to find a complete elbow here. So I'm going to start with the percentage of variance. I think this graph is going to go the other way. So I'm going to start with the percentage of variance. Principal component 1 explains 90%. So it is explaining 95%, right? Then it goes 99.7% and so on. So I'm going to say, okay, these many components are enough to explain all this. I'm just going to choose n minus 1 number of the dimensions. N here is the number of dimensions. So number of dimensions minus 1 will be my ideal choice of principal components or maximum choice. But if the scree plot is telling me that I can limit to with 3 principal components, I can have 99.7% of the proportion of variance explained. I'm going to go with that. So here the scree plot here talks about starts with 1, goes. So this is the part where beyond this, I don't need it. I'm going to discard it. I'm going to say, okay, 1, 2, and 3 principal components are sufficient. All right. So this is what we have for the PCA. This is the data I have. So my objective is to classify it based on the silhouette data. So from the silhouette, we have different informations about scaled radius of gyration, skewness about it, the hollow ratio, the class, whether does it belong to a car, van, bus, or whatever it is, right? So if I say this is about, so this is what I'm essentially going to tag into to a car, bus, or a van. Okay. Now, if I look at this, I'm going to say this as well. I'm going to add this attribute as well. Okay. Let's now describe the data. All right. So we have quite a lot of features. We're going to say shape to identify features. We have 19 features and we have 847 inputs that we have. All right. Now, what are the types that we have? Barring class, everything else is either an int or a float object. I'm going to talk about a very simple aspect, right? So it's going to talk about number of records I have in each bus, car, or van is. We already looked at the class value counts. It says how it going to work. What I'm going to do is just do a very simple, maybe histograms to look at and say, okay, this is what I want to visualize, right? So I'm just going to look at a very few simple visualizations and look at them to see, okay, how's the data distributed? What's the kind of skew the data has? And the reason I'm coming up with this is I want to find out if there are variables that are correlated to each other. I want to first understand the data. Now, if I talk about it, this data has missing values. The data definitely has missing values, and I am going to treat the missing values by using the median imputation. I'm going to take the median value and I'm going to impute the data and say, okay, the reason I'm going from for up to till 17 is nothing but the 18th column is your, the value of 18 here is your class. If I have 0 to 17, it basically means from 0 to 17, which is still hollow ratio. So if it has a missing value, if I'm going to talk about a null value, we are going to talk about a missing imputation. So here I'm imputing with the median value. Now it's going to talk about no missing values. So once I don't have a missing value, I am going to first plot a point. I'm going to just look at how the data is set up to each other. That's going to tell me some kind of an interesting perspective here. Now, if you notice, right, if you notice this particular scatter matrix, it's going to give you an interesting look. I can either do a scatter matrix or I can also do a pair plot. Either way, this is what I'm going to get. But if you notice, I'm going to draw your attention to the fact that almost all the features are going to be correlated to each other. That's something that you're always going to see, and that's going to be an interesting look to have as well.
Fahmi, you said, on the WhatsApp, you said that MissingPy is one of the libraries,
right,
which we use. What are the other ones which are available?
I don't remember that at the top of my head. Nitin, I can share the link with all of you on the group as well. I'll put it up in the Slack chat.
Sure, because I just checked the MissingPy. I think takes out the minimum column with the minimum missing values, and first it fills with the mean, and then it uses the random forest top of it.
Yeah. So the reason is the random NA values cannot be handled. So Python does not handle NA value as it is as an object. It kind of takes some effort on that context. So it fills a mean, then it runs the random forest imputation. I'll look into the algorithm, probably share more insights about it to you. But right now, yeah, that's essentially how it goes. So you kind of will find this specific aspect here. Remember, I told you there is a big amount of correlation to almost all the independent features to itself. If you notice, that's a no-go for some of our algorithms, and that's something that we have to be worried about. So using a dimensional reduction technique here would be the most appropriate solution to solve this specific problem, right? All right, so here we're going to implement the PCA. We're going to take fit and we're going to just plot the implementation. So now if you look at it, all right, if you draw your attention to the screen here, you will find that at 10 you have the highest ideal explanation. So at A6 you have what? For 6 principal components you have 99.5%. At 10 you have 99.7%, and 12 you have a lot more. So you can just print it also and see how it works. But that's the idea. So when you run this cumulative sum with the principal components explained variance ratio, you will find how many number of principal components are required to replace the 19 variables. Ideally here the PCA is telling me that I have 10 variables that I want to replace it by, and if I replace it with 10, I am getting about what, 99.7% of the original information retained, and I'm going to use that. So that's the ideal way of looking at this. If I don't use the cumulative sum, it's just nothing but the ideal is going to be a scree plot. So this is what we call as a scree plot. So either you can use a scree plot or the cumulative variance ratio. So with this, right, with the scree plot, what you're going to identify is where do I cut it off. With the you here it says 2 or 3 is the ideal solution, but in essentially with the cumulative variance explained ratio here, I'm saying that okay, 99.7% is ideal. So I'm going to go with 10 principal components.
Can you just explain this again? Difference between the two?
Yeah. So here the number of what you're going to look at is the scale is minute, so you're not going to be able to understand the difference here. But ideally, the objective that you're going to look at, right? The ideal objective that you're going to look at is to have the highest degrees of principal, highest degrees of variance explained with the lowest number of principal components. So here I say 10 is good. If you notice, with two components, I'm only be able to explain 99%. So that the 99% I have here. Now with this, I'm going to talk about 99.7%. So ideally, I'm saying that okay, 99.7% of the variance is captured with 10 principal components. If I talk just about the scree plot, the scree plot is what we use here to say okay, the number of principal components that require that are required, right? So remember we talked about the eigenvalues to sort and say beyond which I'm going to discard the number of components. This is the discarding of the components. This is used to discard the components, and this is used to identify the ideal number of components that you want to use with that has the highest variance ratio explained. You're not going to be able to use one without the other. Does that clear the question?
Yes. One more thing. Through PCA, we have already converted the variables into into a Gaussian variable and independent of independent of each other. Once we
Correct.
So now, why do we want to remove any of the component and lose information even if it is 0.01%?
Okay, that's a fair question, right? So the reason we don't go with all the principal components is if I take and load my entire set of principal components or the axes, what you are going to get, right, is the exact data set, is the exact variable of the data set coming back into you. So you want to select or give off this cutoff point that says, okay, I have the maximum variance explained. No, just because I'm transforming it, if I reuse all the variables again, I am going to end up with the same data set over, which kind of defeats the objective that I have with the principal component analysis. Does that answer your question?
Yes. If I suppose we don't remove components over here, just in case, understand that it will give me back the same data set.
Right.
So if I don't remove over here, and suppose after that, suppose can I use a linear regression model after this?
Yes, you can.
So if I use a linear regression model, there's an AIC and the AIC values which penalizes the for extra dimensions.
Correct.
So won't it help in that case?
As in using all the components?
Yes. So there won't AIC and because it iterates on the best model fit with the least the values.
Okay, so when you're using a stepwise regression, you're going to choose the ideal features, right? So there is where the AIC will have a major play. So when you're taking a stepwise regression, we say, okay, the step is basically iterating to add or remove variables. You want to do a forward selection or a backward elimination. You want to drop or add variables based on the information value that it kind of carries. So AIC being the lowest is what we'll choose. Now, the variable within it that has the highest AIC that kind of inflates the AIC will be dropped. That's a stepwise regression concept. Now, if you're going to use this data set, right, I'm going to say I want only 10 components and I'm going to fit this out. So your question that says, why don't I use all 10 to let the model choose the best set of features, correct? Ideally, that will not be the correct solution here, given that we just kind of went through the basic idea is, I want to use the ideal number of components. If you understand the math behind it, it's just basically transforming the data. The principal component analysis is kind of setting up data and transforming them into different axes. Now, if that is the case, right, I'm going to transform a data and I'm going to use it in a model and let the model choose the ideal selection. That will not make a more relatively rational sense context there. Because your model selection, the feature selection, you can't just rely on AIC. We are removing the multicollinearity between features, transforming the variable into a different dimension set, and then using that aspect. So that ideally is not going to be a job that you're going to leave completely up to the linear regression. I'm going to use the PCA to say, okay, this makes sense, this does not. So that's how I'm going to limit it and go by. what I'm going to introduce you to is a method that we call as the grid search method. Now, the grid search is to help me identify the best set of optimal hyperparameters. Now, this is not particularly to the feature engineering part, but this is to help you build a better model. Now, this is also a way of finding the ideal solution, or the algorithm essentially is used, which whenever I'm using an algorithm, I'm going to find the best possible hyperparameters of this algorithm. Now, given that, all right, let's say I want to import my support vector machines. Now, what I'm also going to import and fit this model. So I'm going to say grid underscore params equal to. Now, this is what I have. So using this, I'm now going to create a grid search model right now. Okay.
What is this stand for? 0.1, 0.0.
Okay. Remember the cost in your.
No, not that. No, that's the value. My question is, are we searching only on these values?
Yes, we are iterating over these values to get the best possible result from this sort of a grid search.
But then again, we are not taking into account every value. So how do we know that these are the only values that fit the best model?
Okay, so it basically it is about exploration. So this grid search, when you're talking about it, right? So the objective here is I am going to try among all these values for the model as an input to the model, and that's going to come back and say this algorithm, this particular result has the best solution possible. So that's how it's going to essentially work. Okay, if you want to print the entire grid results, you can always do that by making verbose equal to 5. That will print it. I can print the best model parameters.
Gamma was also part of his.
Yeah. So you can also use. So just an example here, Nitin. I'm just setting up an example that shows what are the ones that you can optimize. So with if you take random forest, you have a lot more parameters. You have min depth, max depth. You have this criterion. You have the bootstrapping. So you can choose any one of these parameters. This is just a showcase to see how do you do a grid search per se. Gamma is also a factor that will affect. Yes, definitely it will affect my RBF more than my linear. So the gamma can also be used in case if you want to change or tweak the parameters. Yes, you can. This is just to show you how to work around with it.
If it is not problem, can you use gamma also in slide just to know how to go about it?
Shyam, can you explain the grid params once again?
Okay.
Yeah, 0.1, 0.01, what do they
Okay, so it's basically for if you understand that we have this support vector machines, right? So in support vector machines, you have 3 parameters that we can tweak. One is your cost parameter or C, which will give you either a soft margin classifier or a hard margin classifier. The other factor is what we call as gamma. That's basically how much of your kernel does it fit, overfit, or underfit your current curve. And then we have the linear, and then we have the kernel type. So if you have linear, radial, RBF, and polynomial. So what I am trying to do is now what will happen right now is the fact that it will try for 0.1, and linear 0.1, 0.01, and linear again. So it will try for it will do a permutation combination of all these parameters to the final algorithm. All right, so it will try all the combination of all these algorithms and come up with a final model that has the best result in terms of accuracy and score.
But somehow this again is kind of a manual intervention over there.
Right. So ideally, it's up to us to some point to say, okay, the other option that you can do for SVM is you can go from 0.01 all the way up to 100 between increasing values in 0.1. So you can always do a step in that manner. So that's going to take quite a bit of time to run, but ideally we kind of set benchmark values and we go about it. This may not try for every possible value there. So if you look at that, you'll have 0.1, 0.01, 0.05, 0.03. So you have multiple values that can ideally change your equation. So it is up to the user to see if you want to try it at that level, at that granularity. So this, I might not run this out right now, but if you run this, you'll understand this. It's going to take quite a bit of time because it has to run. I don't know if my machine can support this high intensity, but yeah, the idea is if I run all these combinations, it will take some time for the model to execute and then they come back with the results. And once you print the best parameters by saying that, okay, this is the best parameter, this is what I'm going to finally build my model upon. And that's how it's going to essentially work. All right. You also have this cross-validation score, where you're going to create a k-fold cross-validation and you're going to find the best you're going to see if the cross-validation is actually helping you do a better job in this context. Okay, so if I start running this right now, it's going to run for quite a bit of time. So
if you want, you can remove some of
sorry,
C values. If you can just see, like you can,
sure.
You can remove gamma or if it's taking time. No issues.
Yeah, I think I'll probably leave it and let's see how long it's going to take for running. So once you have the results, right, you're going to have this grid search. You're going to have this GDSR that's going to carry the results, that's the best parameters and best score. Yeah, it's done. Now, if you notice, this apparently seems to be the best solution for the current data set. Now, if you want to know why, you can always print the model score in terms of accuracy and then find out why does it mean or why does it say that this is the ideal solution. So you're getting an 87% accuracy in the result. That is the reason it's saying that this is the best parameter for the score.
This is the same as the accuracy score which we...
Yes. So whenever you execute a model, you have this accuracy score, right? You use the metrics.score or model.score. This is the same as that. Yeah. So this is how you run a grid search per se.
In this tutorial, we have learned about what is unsupervised learning, what is machine learning, and also what is clustering, what is PCA techniques. I hope you liked the video and do let us know in the comment section what else you want to learn from us. And also let me introduce that Great Learning has come up with a brilliant idea, that is Great Learning Academy, where you will get almost 80 plus free courses, and after completing your course, you can claim your certificate as well. And if you want to do these courses in a mobile application, that is also possible using Great Learning app. So go and use the opportunity as much as you can and skill up yourself. Thank you so much.